Yo, what's up, guys? Welcome back, episode 132 today. Yeah, 132. We got a ditto today. Classic one as well. I feel like we're getting a bunch of classics the last couple days. Let's take a look at the ditto sound. There's our sound. Like a little blob on the screen. But yeah. Let me quickly respond to this text. Yep. Let's jump into Leetcode. Man, I feel like every time I record these videos, I'm so tired, and I literally took a 2-hour nap as well, and I'm still tired. Like, um, started my fitness journey. I've been working out, and like, man, I just get so tired after I lift and everything. After I eat, lift, I just get so tired. I don't know. It's because I'm like new to my journey, but man, I'm exhausted. Anyway, let's try and jump into some problems. Let's take a look at this distribute candy among children too. You're given 2 positive edges and a limit. Tell the total ways to distribute and candies among 3 children such that no child can get more than the limit candies. Hmm. I think we've done distribute candies among children 1. Let me see if we have done it. Distribute candies among children 1. We haven't done number 1. Let's do number 1 and then do number 2. But what is the difference? 2 children and a limit. Is it the same question then? No way. The constraints are bigger. We have to think about the brute force solution here. So what would be the brute force solution here? It has to be some sort of backtracking, like combinatorial enumeration. Hint one. Use 3 nested for loops to check all the triplets. Three triple for loops. What is it? Always going to be a limit of 3? Oh, it's always 3. So maybe it would be like for I in range length. It would be range length, range limit, right? Because we don't want any more than 2 candies per children. So for J in range limit, K in range limit, then we want to check, well, okay, we're gonna have output 3. Okay, we're gonna have some sort of count, right? We have some sort of count. We're gonna have what? Where we? Do we create the tuple in here? Or do I create the tuple outside of here? I'm not sure. If I plus j plus k is equal to n, then we increase the count. Fuck, man. How did I not get that, dude? I was thinking about like creating the tuple, like going like tuple is equal to like 0, 0, 0, and then like, you know, editing the tuple or something, but it's like, it was so much easier than we need to do a +1 here, I think. Ugh. have the fastest solution. I'm not gonna look at it though. I'm not gonna look at it. Okay, now we have to figure out the fastest solution for this instead of doing a triple for loop. So how can we get rid of a triple for loop here? There is ways. We've looked at it before. Take a look at the hands. We can enumerate the number. Indians will get it. We go from what would you like? K is equal to I. If I wonder if this will work. Tab count. No. Let me see what this thinks. is equal to n minus I plus j. N minus I plus j. Instead of this, we can do 0 is less than or equal to k, but is less than k. Oh, we equal to limit. Then we do count plus equal to 1, we return our count. Will this be fast enough? And then squared solution does it have to be faster? Maybe we can add dp to it. So we have to use a combinatorics way.
Hey everyone, and welcome. Today we're tackling a Leetcode problem called Distribute Candies Among Children 2. It sounds sweet, right? We'll break down how to figure out the number of ways to share candies with a few rules. Let's dive in. So here's the deal. We're given a certain number of candies, let's call it n, and a limit. We need to distribute these n candies among exactly 3 children. The main rule? No child can get more than limit candies. They can get 0, that's fine, but not more than the limit. Our goal is to count all the different ways this can be done. For example, if one child gets 2, another gets 1, and the third gets 2, that's one way. If they get 1, 2, 2, that's a different way if we're considering which child gets which amount. The constraints tell us that n and limit can be pretty big, up to 1 million. Let's look at an example. Say we have n equals 5 candies, and the limit is 2 candies per child. How could we figure this out? Well, let's think about the first child. Can they get 0 candies? Yes. If they do, we have 5 candies left for 2 children, each with a limit of 2. That means child 2 could get 2, and child 3 would need 3, but that's over the limit. So child 1 getting 0 doesn't work out easily. What if child 1 gets 1 candy? That's within the limit. Now we have 4 candies left for the other 2 children. Child 2 could get 2 candies. That's the limit. Then child 3 gets the remaining 2. So, 1, 2, 2 is a valid way. What if child 1 gets 2 candies, and a C_1 candies left for the other 2 children? Let's call this remaining underscore candies. Now for the second child, say, C_2. They also can't get more than limit, and they can't get more than remaining underscore candies. But there's another constraint on C_2. The third child, C_3, will get remaining underscore candies minus C_2, and C underscore 3 must also be less than or equal to limit. This means remaining underscore candies minus C underscore 2 must be less than or equal to limit. Rearranging that, C underscore 2 must be greater than or equal to remaining underscore candies minus limit. Of course, C underscore 2 can't be negative, so it's at least 0, or remaining underscore candies minus limit, whichever is larger. So for a fixed C underscore 1, we can find the valid range for C underscore 2 and count how many options there are. This is faster. Here's how that logic might look in code. Conceptually, we'd have a loop for the first child's candies, C underscore 1. Then we calculate remaining underscore for underscore 2, underscore and underscore 3. The minimum C underscore 2 can take is the larger of 0 and remain.
Tough explanation. Let's take a look at some solutions, maybe. Min first, so we get the max of 0 and minus 2 times limit. Min and limit is equal to 0. Fix the first child value. Okay, so we count min first. Min first is equal to the max of 0, n minus 2. N minus 2 being that we have 2 other people to give candies to. And then we times that by limit, right? And then we have our max first, which is equal to the min of n and limit. Then we have our count variable. Then we go for I in range, length, min first. No, we don't need the length. We're already gonna have a number. Min first, max first, plus 1. We simulate our first value, which would be n minus I. Right. Because n being the amount of candies that we have, right? And then we would simulate the other two. Min C2 is equal to the max of 0 and n minus limit. We picked the second one. Min C3 is equal to the min of n and limit. Count plus or equal to min C2 minus I would have never got this by myself, like this solution right here. Would have never got it by myself. So I just want to put that out there. I'm gonna add a little note here. Did not get by myself. Learn combinatorics. So if I come back to it, I don't feel bad that I can't solve it. Yeah, the combinatorics like just really confused me. There's no way. It's just confusing, man. Study planted. I really want the Leetcode 75 badge, man. We are very close, dude. Take a look at edit distance again. We have solved this May 17th, so it's been about half a month. Ooh, let's reset this. Okay. Chest, that's so bad, dude. Word 1 and Word 2 return the minimum number of operations returned to convert Word 1 to Word 2. You have the following 3 operations permitted on a word. Insert a character, delete a character, replace a character. Okay. So, looking at this problem, I instantly think about states here. So, we have an insert state, a delete state, and a replace state. Replace H with R. So, how do we know to replace H with R, though? That's the thing. I think our base case would be like, if I is greater than or equal to the length of word 1, and J is greater than or equal to the length of word 2. I'm going to leave it as like return for now, right? And we're going to have 3 states, right? Replace. Replace, right? So okay, well, let's do if word 1I is equal to word 2J, right? Then we're just going to backtrack I plus 1, J plus 1, right? Else if word 1I, I guess we'd have an else here. Probably an else. We do if it's not equal, right? Which would be all of them. Okay, so we can either replace H with R. Okay, so we can do, well, let's do insert. We need to insert a character, which would be given two strings, word 1, word 2, return the minimum of operation required to convert word 1 to word 2. Okay. So what would be insert? Okay, if we were inserting, we would do backtrack I plus 1. Because we're inserting, right? We'd keep J the same. Insert is equal to backtrack I plus 1, J. Insert delete is equal to backtrack. If we were to delete a character, what would delete look like, dude? No, we can replace. I know replace should be, we would just move both. I plus 1, J plus 1. There's obviously a DP problem, so we'd have our DP out here. Alright, we'd probably return 0. We'd probably do a DP part, which would be if IJ in DP, DP IJ DP IJ, right? Then we'd probably do like the min of D. Well, they'd all be 1 plus, right? 1 plus. 1 plus. Backtrack. We do, okay, DP IJ is equal to the min of insert, delete, replace. And we would do DP IJ is equal to ands. Probably return ands. That's not even gonna work. We didn't even finish this. I know we're missing this one. I know that. Damn, we were really close in the way we were thinking about it. We got dpij. We have if word I is equal to word 2j. Whoops, we should have done and is equal to backtrack. I plus 1, j plus 1, right? We did our inside. We did our inside correctly. Oh, no, it was the other way. We would go from I. Why would it be j plus 1, though? Delete would be I plus 1, j. Then I plus 1, j plus 1. Yeah, replace. Well, dpij is equal to ends. We return ends. Backtrack 0, 0. I think it's out of range. And that's why we're getting the issue. I think it's the length of wood. We really close thinking about it the way we should have with states, which is good. Counting bits. I think maybe we just do like leave that for another day, and we do like a graph theory problem. Always love the graph theory problems. Reorder routes to make all paths lead to the city 0. I think this was a tough one when I looked at this last time. Take a look at all paths to source node. Did this about nearly 2 months ago. Given the directive to the graph DAG and nodes labeled from 0 to n-1, find all possible paths from node 0 to n-1 and return them in any order. So graph 0 has 1, 2. Node 2 has 3. Node 1. It's 3. 3 doesn't go anywhere. There's a directed edge. Okay, given the directed edge, DAG. Or n-1. Find all possible paths from node 0 to node n-1. Return them in any order. Right, so we could go 0, 1, 3, 0, 2, 3. Okay, that makes sense. A directed acyclic graph. Directed acyclic. That do not form cycles. In simpler terms, a DAG represents a relationship between elements with direction. Okay. My first thought is BFS here, but I think you can use both, to be honest. So let's just do def adjacent list, passing out edges, right? Nodes we do for I in range length edges. We would do, well, graph I is equal to this. Then we do, okay, for edge in edges. Graph edge edge. Man, I don't know. Graph source is equal to source dot append edge. Return our graph. This needs to be indented a little bit. List. Let's do ADJ list is equal to that. Let's print out ADJ list. Edge in range length edges. We do graph source dot append edge. I don't know why I don't get it every time. fuck is this? Why can't I build? Okay, so then we would do def DFS. We want to pass in our node. We want to pass in our let's do array. Okay, so we would go, alright, well, we want everything from node I. So really all we have to call from is backtrack 0, 0, right? From node 0, and we pass in an empty array, right? I think we're probably going to need like a res so we can return, right? Because we're expecting a list of a list. So we'll need a res. We'll loop through. And we'll go, okay, well, if let's add a visited. I'm trying to think here. So we would do DFS. We're going to pick one edge, do this. We get there. We know this doesn't have any cycles, so we don't really need to check for that. We know we can't get back to 0, right? So maybe we don't really need the visited array. If node is equal to 0, 1, 2, 3. Let's do target node. The length of nodes, the length of, sorry, graph. Let's do -1. Is that gonna work, dude? Dude, let's do like target node is equal to the length of graph -1. Okay, we'll do target node here. Well, if node is equal to target node, target node, then what do we want to do here? So if it's equal to the target node, then we just want to probably res.append array.copy. We return here. This will be our base case, right? Otherwise, we loop through our neighbor for neighbor in graph node. And we call DFS on our new neighbor, right? So we do neighbor, array, target node. Okay, we probably want to append here, so let's do array.append node. We append loop through neighbors. Neighbors. Okay. Do that. Get this. I think that should work. Get that, and then we just return res. Backtrack is not defined. Okay, called. Let's just call it DFS. Why not? Array target node is target node. Zero one. I think we need to append first when we get to the node. Zero one three. Zero. How do we go 0 1 2 3? How does that work? I think we're gonna need a visited. I think. Visited. Visited is equal to set. Pass in our visited. Okay, we can then check here. Well, if neighbor not in visited, then we can do this. Oh, we need our visited to add neighbor. Zero one three. Don't get the other one. I think we don't get to 3. Right. I think the visit array is messing it up. It's not getting to the last node. Yeah, you need to remove visited nodes. That's what I was thinking. Generally, dude, I don't know what is wrong here. Like, I don't know how to do this part. Oh. I'm referring to graph node here, but this should be adjacency list. Whoops, dude. So apparently I need to pop here. But as well as pop down here. Interesting. It's probably way too much code for like this question. Let's see what I did last time, because I bet you it's way, way smaller. We did a BFS, the Q. It's an interesting way to do it. How do we do this way? We did BFS again. This we do DFS here. Okay, we do DFS here. Did a little bit of a different way, but it's alright. But yeah, we solved that problem there. So making some progress on this graph theory one. Got a few more to look at, but yeah. We're gonna call it there for today. Appreciate you guys watching, and I will see you guys tomorrow evening. Start working tomorrow, Monday. So, yeah, I start working Monday. So it'll probably be shorter videos throughout the summer. Probably about an hour long. I'm not gonna lie. Like, it's gonna be hard to do 2.5 hour videos when, I'm out all day. So, I'm gonna be tired when I get home. Make a video. Make lunch for tomorrow and everything. So, but yeah, probably for the next 8 weeks, it'll probably be hour-long videos, and then we'll kind of get back into some longer videos. Maybe every now and then, maybe when I'm here on the weekends, it'll be a little longer. Maybe some nights I'll do 2 hours. I don't know. We'll see. Maybe some nights will only be one problem. So who really knows? But yeah, I just appreciate you guys watching and following along my journey, and I will see you guys tomorrow.